Okay, now we're going to be talking about power functions that have negative exponents. And before we go into that, let's recall that anytime you have a negative exponent, x to the negative 1 power, fraction bar, bring that to the bottom, that's the same thing as 1 over x to the positive 1. That's how we remove negative exponents. And we do have a basic shape of that f of x equals 1 over x. That's one of our parent functions. And this is called a reciprocal function. Reciprocal function. Because we reciprocated that x to the negative 1 in order to give us 1 over x. Power functions with negative exponents are undefined at 0 because that's going to bring our x to the bottom, and we cannot divide by 0. We can't have a 0 on the bottom of a fraction. Therefore, they will contain discontinuities. Notice here that you have infinite discontinuity. You have infinite discontinuity here at x equals 0. It increasingly gets closer and closer and closer, but it never crosses that discontinuity, and it can't because if it did, it would be dividing by 0 there. So let's graph some of these and see what they're going to look like. Again, our first one, 4x to the negative 2, reminder that that's going to be, we need a fraction bar, bring it to the bottom. The same thing as graphing 4 over x squared. Plug some points in, and again, notice we are going to have discontinuity at 0, and it is going to be infinite discontinuity. So on these, if you would like to go ahead and draw you a vertical line just to show that discontinuity, that asymptote line, as you will, that we're going to have with this graph, you can. And now, and there you see it, and now that we've drawn this this asymptote line, let's go ahead and plug in some values for these x's and see what we're going to get for y's. And here you see that I've plugged in values on the right side of the asymptote line. Plugged in 1, got 4. Plugged in 2, got 1. Now notice something. As we plug in fractions, we're going to have to square it, and then we're going to have to divide by it. So we're going to have to flip and multiply. So when I squared 1/2, got 1/4, and did 4 times 4, it gave me 16. So as we get closer and closer to this line right here, as we get smaller and smaller, we're gonna shoot up to infinity there. Now, when I plug in values like 4 and I square it on bottom, 4 squared is 16. When you do 4 divided by 16, you get a fourth. However, if you were to plug in values like 7 and 8, plug in 8, you'd have 8 squared on bottom, which would give you a 64, and 4 out of 64. Well, that gets smaller and smaller and smaller because 4 64ths, 4 hundredths, 4 thousandths, and stuff like that. You're getting closer and closer to 0 as you travel to the right. Now let's plug in values on the other side of our x equals 0 and see what happens there. And notice when I do that, I actually get the exact same values except for negative. And that does make sense because this is going to have rotational symmetry, and that's the reason that happens. My domain here, x can be all things except for 0, so I'm just going to put x cannot be 0. My range, notice that I do have an asymptote here as well. I approach 0 from above and below, and we talked a little bit about y. As we go to infinity, that's going to approach 0. So therefore, my range, y, will never be 0 either. My x-intercept and my y-intercept, there are no x-intercepts and there are no y-intercepts on this graph. Increasing intervals, my graph decreases on this side, and then it jumps up here and it starts decreasing again. So there are no increasing intervals, not applicable. My decreasing intervals decreases from negative infinity up to 0. And then it jumps up here. Now, you got to be careful. You can't say it decreases from negative to positive infinity because it doesn't. It decreases from negative infinity to 0. Then it actually jumps up at 0, and it starts decreasing again. So it also decreases from 0 to positive infinity. Your symmetry, this does have rotational symmetry, so it's symmetrical about the origin. Discontinuities, you have a discontinuity at x equals 0, and that's going to be infinite discontinuity at that point. In behaviors, as x approaches positive infinity, notice that it levels out to a value. It doesn't go up forever or down forever. Y actually approaches 0. And the exact same thing happens as you approach negative infinity. The graph levels out to y equals, or y gets closer to 0. The next graph, we have -1 times x to the -5th power. So that's going to be -1, bring the x to the -5th to the bottom, make it x to the +5th. Plug in some values, see what happens. Let me scroll over so I can do me a t-table. Okay, so I went ahead and drew my same x equals 0 for a vertical asymptote there and y equals 0 for a horizontal. Notice as I plugged these values in, when I plugged in 1, I did get -1, but when I plugged in 2 or 1/2, I got things that was not going to be graphable on this graph. And the reason being is whenever I plug in 2, again, I get -1/32, which is so tiny that it's pretty much right there on the x-axis. When I plugged in 1/2, I got 1/, because when you do 1/2 to the 5th power, you get 1/32, flip, multiply, and you get -32. So it's going to be so far off your graph. So you're basically getting the exact same graph. It's just growing pretty fast. And then with your when you plug in your negative values, you're basically going to get this exact same thing, just in a different quadrant. And there you see those negative values plugged in, and you actually jump over to the second quadrant and have the exact same identical graph, just rotated. So your domain here, x can be all things except for 0, and you're going to have the exact same thing happening with your range. You do have vertical and horizontal asymptotes there. Your x-intercept, there are none. Same thing for your y-intercept. It will never cross the x or y-axis. Increasing interval, this one actually increases from -infinity up to 0. And then it jumps because of the infinite discontinuity, which we can go ahead and actually put down here. And it's going to start increasing again from 0 to infinity. So that infinite discontinuity was at x equals 0, and it was, again, I said infinite. Decreasing interval, again, that was not applicable. There was none. Symmetry, this does have rotational symmetry or symmetry about the origin. And finally, end behavior. As we travel to the right on our graph, again, notice that we're getting closer and closer to that x-axis, so y approaches 0, and the same thing happens as we travel to the left. Next problem, we have 3/2 x to the -3. And what you can do here is that x to the -3, if you'd like to write it up there with the top, because it's 3 or x to the -3 over 1, you can write it like this, and then that would bring your x to the -3 to the bottom. So that's going to be the graph that we're graphing here. You will have a vertical line at x equals 0 that is a point of discontinuity. For your graph, x can't be 0. And I went ahead and drew the exact same horizontal. You're going to have the same horizontal asymptote line there. Now let's do us a table of values to see what happens everywhere else. Okay, and there you see your points, and you kind of see the same thing that's been characteristic with all of these. Since it was a positive 3/2, it looks very similar to your other x to the negative powers. As well, as since it's a positive 3/2, you don't have any type of transformations. Your domain, x can't be 0. Your range, y can't be 0. You do see those asymptote lines there. There is no x or y intercepts. Increasing or decreasing. This one's decreasing pretty much everywhere except for at x equals 0. It does jump up to the other quadrant there. So it decreases from -infinity up to 0, and then from 0 to +infinity starts decreasing again. Symmetry, this is symmetrical about the origin. Discontinuities at x equals 0, you do have, again, infinite discontinuity. And end behavior. Travel to the right, and as you travel to the left, your graph levels out at a constant 0 value. So y equals 0 is going to be, or y approaches, not y equals. Y approaches 0 as you travel to the left and to the right. Okay, number 4. We're graphing here -2x to the -4, which would again be -2 over x to the 4th power. Notice you have your negative coefficient out there, so it's going to look very similar to our second one that we graphed. Let's create a little table of values and plot some points. And there's a kind of look at what your graph would look like. Again, you do have those same horizontal and vertical asymptotes, so x is not going to be 0 and y in these cases are not going to be 0. Your x-intercept and y-intercept, there are none. And again, if you think about the reason why, x is never 0, y is never 0, so you can't cross the x-axis or y-axis. Increases from negative infinity to 0, and then continues increasing from 0 to infinity. Decreasing, there are no intervals. Symmetry, this does have, again, origin symmetry. So you pretty much have the same thing over here. Discontinuities, at x equals 0, you have infinite discontinuity. And then in behavior, as you travel to the right and as you travel to the left, your y value levels out to 0. Okay, and the last one. Pretty much the same thing. Negative 1/2 x to the negative, or negative 1/4 x to the negative 6 would be negative 1 over 4 x to the 6th. Table of values. And you have basically the same graph. So I went ahead and have filled everything out. Again, your domain, x or y can't be 0, your range. And there is no x or y intercept. It increases from negative infinity to 0, and then from 0 to infinity, it increases again. Decreases never. Origin is your symmetry. It's symmetrical about the origin. Discontinuity at x equals 0, and that is infinite discontinuity. And the exact same end behavior the other ones have had.